Okay, so we left off and we worked through an example in Excel where we're building confidence intervals for a sample mean, or really using our sample mean to build a confidence interval for the population mean. So we said we could do the same thing for our sample proportion, which we have the equation for that standard deviation of my sample portion, or the standard error, which we were going to calculate using this formula. So let's take a look and see how we do this in Excel. All right. So anytime I'm thinking about a proportion, when I'm looking at actual data, a proportion is going to come from a variable that's 1, 0. Okay. So anytime we have the 1, 0 variable, which last class we kind of changed the original variable, I think it was like more than 10,000 students. And we said, okay, let's create this indicator using the if statement where we put a 1 if the school has more female than male undergraduates, and we put a 0 if they have more male than female undergraduates. So this variable essentially, well, there will be a 1 if they have more female students. So we could find the proportion of schools that have more female than male students. How would we do that? Well, I would count up the number of schools that have more female than male and divide it by the total number of schools that I have, right? Well, when we're doing a mean, we go all the way back and think about what we're doing. We're adding up all the values for X divided by the total number of observations we have. Well, if the variable is 0, 1, notice it would look something like this. Right? I'd have a bunch of 1s and 0s added up, but the 0s don't impact anything. So that numerator really just tells me the number of 1s I would see for that variable, or the number of schools that have more female than male students, and then it would divide that by the total number of schools in my data set. So if I find the mean of a 1, 0 variable, essentially that's going to give me the proportion, right? The number of 1s divided by the total number of observations. So here, we can kind of think about my mean proportion, right? Or my sample proportion. I can simply use that average function for this 1, 0 variable, Control Shift or Command Shift on a Mac, hit Enter to go back up to that cell. And I see 63% of schools from this sample, or 63%, a proportion of 0.63 or 63% of schools have more female than male students in this sample, okay? I can then find my sample size using what function? Count, right? So I just go over, Control Shift down arrow, Command Shift down arrow on a Mac, hit Enter. So I've got 111 observations, so that's good. It matches up, working with the same data. And I've got my mean proportion, my sample proportion now. Okay. So proportion, your sample proportion is really just the mean of a 1, 0 variable. That's one way to think about it. So we built all these confidence intervals down here last class. Similar here, I'm going to just calculate the intermediate value. So I'm going to find the standard deviation of my sample proportion, just because I think it's a little bit easier to put this formula into Excel than this one. I don't know. It's up to you. If you don't want to do this, you know, do it all in one cell. But I think it's a little bit easier, so I show it to you this way. So that standard deviation would be the square root of my sample proportion, right? If I can move this guy out of the way, times 1 minus that sample proportion. So just click on that again. And then divide that by my sample size, right? So all I'm doing here is, right, putting in this equation to solve for that standard deviation of my sample proportions. I'm just putting this into Excel. I'm having Excel do the math for me instead of having to worry about how many decimal points do I go out. Like on the homework here, I can just click on the values, right? Any questions on this? Well, now I've got my sample proportion and the standard deviation of my sample proportions. So I've got really the two of the components up there in that formula on the board. The only thing left I need was, well, whatever level of confidence I want, I need to make sure I'm choosing the z-score that gives me alpha over 2 on either side of my confidence interval. So we said, okay, we got to find the z-score. We're working backwards. We know the area in the tail. So we're going to use that norm.s.inv. We know the area we want in the tail is alpha divided by 2. But what's one other problem I'm going to have here? We talked about last class. Yeah. Yeah, if I hit this right, I'm always going to end up with a negative. And we said we don't want a sign associated with that z-value because it's already built into my confidence interval, right? I go to the right, positive, however many standard deviations away I need to go to my upper bound. And then I go to the left, where I subtract a certain number of standard deviations away to get my lower bound. So those are already built into my equation. So we said, I think last class I showed you both ways, right? You could do 1 minus alpha over 2. You know that because it's a symmetric distribution, that would give you the same value but positive. Or we could use that absolute value function. I usually use the absolute value function, honestly, just because it's easier to type. It's pretty, kind of reminds me that, oh yeah, I need the positive value. Excuse me, sorry. So this should, we copy it down, give me the z-values I need to build the next 2 confidence intervals as well. Now notice, when I'm looking up this z-value, it's the number of standard deviations where I need to go to get alpha over 2 in the tail. So the values I found here should have been exactly the same, right? Because I was using the same alphas in the problem that we used last class. So I could have copied those over if I really wanted to, but I thought working through this today would be good to like remind ourselves we need to use that norm.s.inv function. Okay. Any questions on that before we keep moving? Now from here, it's pretty easy because we have a pretty simplified lower bound equation. I just take my sample proportion, I subtract the number of standard deviations away I need to go, multiplied by the standard deviation of that sample statistic, which in this case is the sample proportion. Okay. Now, if I copy this down, what do I want? It's the only thing I want to change when I'm constructing a different level of confidence. Alpha, right? Which has its kind of corresponding z-value. So I'm going to freeze everything else, F4 or Command T on a Mac, except for that cell reference that's using the z-value associated with different alphas. Okay. So now when I copy this down, if I'm wanting to say something with a higher level of confidence, what should be happening to my confidence interval? We said last class it would be getting, intuitively, yeah, it gets wider. And why? Well, because I'm wanting a smaller area in the tail. So if I want a smaller area in the tail, that's a larger in absolute value z-value, which increases that margin of error. So I'm adding and subtracting a larger value to making my confidence interval wider. So when I copy this down, hopefully the lower bound is getting lower. Sure enough, it is. I then said you could type it in again, but a real easy kind of way to do this is I want the exact same thing, the exact same equation for my upper bound, right? It's that exact same formula. So I'll copy this, hit enter to get out of the cell, paste it. Oops. All right. So it's the exact same thing, but I want to add that margin of error to my upper bound. So everything else is the same. I just changed that subtraction to an addition sign, copy this down. Sure enough, my upper bound is getting larger, right? So I'm getting a wider interval as I go from the 90 to the 95. Right? So 90%, 95%, the 99% level. Okay. Any questions on this? So, I think this, it's pretty similar, right? The equation is a little bit different for our sample proportion, but really not too bad. And I'll probably, you have your individual assignment, connect assignment due today, correct, at the end of the day? So I'll probably, on Monday, I'll probably wait till after class on Monday, probably put the next Excel assignment up there. But it will be kind of related to confidence intervals. Okay. At least the first part of it will be. And it'll probably be like the due date will be kind of a ways off, but I'll get up there early so we can start working on it. Any other questions on this before we kind of leave Excel? So I had left some things up here that we had already worked through, just like examples of using the inverse formula. So when you look at the full completed file, these might look a little like I had some things up here, but we already did that with the Indiana weather data. Like I showed you how to use the norm.s.inv. So this was just an old folder where I had a bunch of work in it. But I really wanted to just kind of use this data set to focus on these confidence intervals. Yeah. Yep. So if you just try to copy it over, so notice I copy pasted it. If I were to just drag it over, it updates that Z value reference. So I want to make sure that it does not do that, right? I want to keep that in column P. Right? So if I just drag it over to copy it, it updates that cell reference. I'm going to have an issue. One way to avoid that, and I thought I mentioned this on an earlier thing we did, if I go in and hit copy and then I paste it, that, oh God, that's not going to work, is it? There we go. Right? If I copy then paste, it doesn't update any of the cell references, even if they're not frozen. Yep. Any other questions before we jump back into the slides here? All right, something else I want to show you. So like with 10 minutes left, I might stop. I have, let me make sure I brought it with me. I'm pretty sure I put it up on Canvas if I didn't bring it with me. Is this it? Find out. Yes. So I will show you this at the end of class. But for now, I need to bring up another topic. So I mentioned this, I think, it was either last class or on Monday. But it's kind of weird that we have all these examples where we, we have a known population variance, but somehow we don't know what the population means, right? So more kind of, I guess, real world would be we don't have the population variance and we don't have the population median. Right? So what happens if we don't know what that population variance is? Good question. So most of the time we don't know. Well, basically we're just going to approximate that population variance with a sample variance. Okay. So all we're going to do is approximate that population variance with a sample variance. So before, let's see if I can draw this up here. We can kind of piece this together. So before, when I had a sample mean, I took that sample mean value, I subtracted the population mean, and I divided by the standard deviation of those sample means to know as the square root of population variance over my sample size. So if I want to do the same thing, right, but I only have a sample variance, right, it's going to follow the exact same structure when I'm trying to create this z-score. I just use this sample variance, and we reference the denominator now. It's still the standard deviation of our sample means. It's just we use the notation of S instead of sigma to reflect that we didn't use a population variance to calculate it, we used a sample variance. Okay? So the problem is, I'll get to this slide in a second. These won't, if I converted a value into a z-score using this method, I don't actually have a z-score. Because remember, the only reason it's a z-score is because by subtracting the mean, dividing by the standard deviation, I was producing something that follows standard normal distribution. Here, because the population variance can actually observe every observation, think about it this way, it's dividing by n, whereas we in our sample variance are dividing by n minus 1. Right? When we actually calculate the sample variance going back to like week 1 or 2, we're dividing by n minus 1 if it was a sample. So the problem is you have inherently built in that your standard deviation is going to be a little bit off of the true population. So like, let's assume that you treated your population data like it was like, that was your sample. Well, you're dividing by, instead of 100, you'd be dividing by 99. So you're dividing by a slightly smaller number. So that means that your standard deviation on your sample means, if you're using the sample variance to approximate the population, will always be a little bit higher. So instead of z values, we call these t values, right? Now they still follow Well, I'll erase the map up here. So I think this is important. I want to get this across before I kind of. So for now, just take me a minute. Like, trust me that these are called t-values. Right. So when we were originally looking at a standard normal distribution, I think we had something like, we knew the area of 0.025 in the right tail would be the area to the right of a z-score of 1.96. Okay. Well, these t-values, when we use these sample variance as our best approximation, are going to be normally distributed, same kind of idea, as long as we have a sample size over 30. However, we know that the variance or the standard deviation is going to be a little bit greater, right? So instead of having a mean zero variance of 1, we're going to have a mean zero variance of something slightly higher than 1. So it's going to have a higher variance, which means it's pretty bad, but more spread out, right? So here's kind of my student t distribution, which now means if I use that same value of 1.6, what's true about the area to the right of 1.96, but under that t distribution? It's going to be greater than that old 0.025. Notice it includes all of that area plus some additional stuff. So if I still want to build a confidence interval where I have alpha over 2 in each tail, then I can't use 1.96 as that t-value that would give me 0.025 in that right tail. I would need to choose something kind of further out. Maybe, I don't know what it ended up being, 3, 2.5, something over to the right, right? Because the area to the right of 1.96 is much greater than 0.025 for that student t distribution. So we're going to use the same process to create confidence intervals. The problem is we can't use that standard normal table to find these z values anymore because we don't need z values, we need these t values. Right? So we've got a new distribution. We're going to have a new table. I uploaded to Canvas this morning, and I'll kind of take a look at it here in just a second. So is there any questions over, is that clear why the values that we need are going to be different for that student t distribution? And it really comes from the fact that we know our variance is going to be a little bit higher because we're using this sample variance as the best approximation. Questions on that? So, yeah.
What is it called, the student's t distribution?
So, I told you a really dumb story a long time ago about a guy who worked at Guinness. Do you remember what I said about him? So I think his name is Cassette. He didn't have any formal training. So not only did he come up with figuring out that a Poisson distribution was like kind of the theorem on that, he also discovered that if you're only using sample variances to approximate the population, you actually don't end up with a standard normal. And he kind of named these distributions, but he didn't have any formal training like education. And so they just call it the student distributions, right? That's, you know, they're going to take that for a fun fact for a party. So we've got these student t distribution, but we could have several of them, right? Because how much higher is this variance? Well, think about it this way. When I'm dividing by n minus 1, if I've got like n is 1,000, divided by 999 instead of 1,000 isn't going to change this very much, right? You know, if I divide it by 1 less, n minus 1, it's not going to change it much. But if my n was something like 2, dividing something by 1 instead of 2 is going to greatly change how far off I am. So when I'm at really, really low sample sizes, we're going to end up with a really, really wide distribution. As the sample size gets higher and higher, well, the fact that I'm using a sample variance to approximate it doesn't make as much of a difference. And so as n gets higher and higher, we actually get closer and closer to that variance of 1, or closer and closer to a standard normal distribution. So technically, right, there is a family of these student t distributions. Every single sample size follows its own student t distribution. So as the sample size gets smaller, they're more and more spread out. As the sample size gets larger, that variance gets closer and closer to the standard normal variance of 1. So we can kind of think about how we're going to identify what student t distribution we're looking at is going to be based off of n minus 1. So we'll call that degrees of freedom. Honestly, I do think it'd be a little bit easier if we simply label these by the sample size, but by practice what we do, and this will apply to some of the stuff that we talk about after hypothesis testing this class, we'll have this degrees of freedom. You know, it's related to this idea that we're kind of dividing by n minus 1 here. If you want to think about it that way, it can also be explained as we're calculating a statistic using another sample statistic in kind of factoring to a denominator. So it's another way, a reason that's why we say we have degrees of freedom of 1, because we use one statistic to calculate the other. But we don't have to know exactly why or what the degrees of freedom is here. Think of it more so as though it's just identifying what student t distribution you need to use. Right? It's really what it's in practice doing is identifying the probability density function that you know your distribution would follow. Now, we don't want to integrate that function, just like we didn't want to integrate the standard normal distribution. And so we have a table that kind of allows us to look up different student t distributions depending on the sample size, which then kind of dictates what our degrees of freedom is. I'll usually abbreviate that with DOF. So, you know, I kind of drew it out. I didn't necessarily specifically say it, but it ends up being a normal distribution. It's not standard normal, but these t values, any student t distribution we look at, they are going to follow a normal distribution, so they will be symmetric, right? However, they're going to have a variance that's slightly higher than 1. So they'll still have a mean 0, variance slightly higher than 1. And really, as we go to higher and higher sample size, as I said, it's going to become, you know, the variance is going to get closer and closer to 1, or it's going to become closer and closer to a standard normal distribution. So in practice, we'll take a look at the table here in a second, but usually if we're working with anything that has degrees of freedom of 100 or higher, we can just use the normal distribution as a very close approximation. So let me open this up here. I don't think I did before class. So I've got, I think I just threw it over here. So under the Files tab on Canvas, there should be a new PDF called T-tables, right? So these T-tables work a little bit differently than the standard normal tables, okay? So the first difference is the area that we're looking at, we're no longer thinking about the left side of the distribution. Everything here is kind of phrased or is set up in terms of the right side of the distribution. Now that's okay because it's symmetric. So any value we see here for the right side, we know if we were looking at the left side, it'd be that exact same value, but negative, right? So here we can only look up 6 different areas in the tail. So, you know, when I was looking at my standard normal, I've got, I don't even know how many, however many rows times however many columns. I have a ton of probabilities to choose from, right? Well, we primarily, oh, I didn't mean to do that. Primarily when we use a student t-table, we're usually looking at it because of we're building a confidence interval or doing some hypothesis testing. So we're usually kind of concerned with these benchmark values. So 0.2, 0.1, 0.05, 0.025, 0.01, 0.005. Those are the only 6 values we can look up for that area in the tail for a student t-table. Here are our degrees of freedom, right? So let's say I had a sample size of 35. My degrees of freedom would be n-1, so 34. I could then say, all right, what is the t-value that would give me alpha over 2 in each tail? So let's say my alpha is 0.1. 0.1 divided by 2 is 0.05. So I had degrees of freedom of 34 to get 0.05 on each side of my confidence interval or in each one of my tails. I need that t-value of 1.691, which I think the one that we would use if it was a standard normal was what, 1.65 or 1.645? I guess we found out earlier with a connect problem. Okay. So notice as I go to smaller and smaller sample sizes, for that same area in my tail, I'm going to need a larger value. And that's just because it's becoming more and more spread out. Right? So when it becomes more and more spread out, to get that same area of 0.025, we're going to have to look at a value that's a little bit little bit greater. Any questions on that? Yeah.
So I just want to clarify, so the degree of freedom is basically like the sample size.
Sample size -1, right? So the reason why you identify it a little bit differently is because you can think about the lowest. If I had a sample size of 1, I can't actually calculate a sample variance, right? Because that would be 1 minus 1. So that's essentially, it's accounting for the fact that I need a sample of at least 1, at least 2, right? I can't take a sample size 1, I need a sample of size at least 2. So then it kind of is identifying the very first sample you could take is actually, and my degrees of freedom of 1 would be 2 minus 1. Right, and give you that degrees of freedom of 1. So kind of starting out point is degrees of freedom 1, which really is a sample size of 2, right? Because we can't, sample size of 1, we can't calculate a sample variance from that. Because 1 minus 1 is 0, and that does bad things. We divide by 0. So we'll discuss the idea of degrees of freedom a little more once we get to regression. I think it'll make a little bit more sense in the context of regression. But for now, just know that it follows n minus 1. Okay. Any other questions? So the other thing I wanted to point out was at that same area in the tail, if I keep going to higher and higher sample sizes, I said we should approach the standard normal distribution. So to get that area of 0.05, we should eventually get to something that's really close to that 1.65, or out to the third decimal, because this student T table goes out to the third decimal, something that approaches that 1.645 that we actually started out class with talking about the Connect homework. So sure enough, I keep scrolling down. Once I get to a sample size of 100, notice I'm at 1.66. So I'm getting pretty close. Notice my table starts to make really big jumps here because I can't get all the way up to 1,000 without having like pages of this thing, right? So it starts to kind of make jumps. And when we work through examples, I'll probably show you a couple where we have to use the table and kind of use an estimate or kind of whatever we're closest to. For the exam, I really won't give you anything that's over 100 unless I give you something so obnoxiously large, like 5,000 or 6,000, that you can say, well, actually, at sample size of 5,000 or 6,000, I can just use the standard normal to approximate this. Because notice, when I'm at observations of 1,000, 1.646 instead of 1.645. I'm only off at the third decimal point from the standard normal there. So I can get a really close approximation just using the standard normal, which is what this last row actually reflects to us. This last row, so as the student T distribution approaches the standard normal, looks more and more like it. In order for it to be exactly equal to the standard normal, I need an infinite number of, and that kind of comes from the fact that like, if I divide by infinity, infinity minus 1, right, is still like an infinite set. So like that's why I'm actually to infinity before that student T becomes the standard normal, right? But anything over 1,000, you can see, I mean, we're not even off to the third decimal for some of these desired areas in the tail, okay? So anything over 1,000, we can use that standard normal distribution to approximate, which is representing this last row. So even though we can use the Z tables to find like what Z value would give me 0.025 in the tails, I can also use the student T table and just use this last row. Notice if I go 0.025 in the tail and go to that last row, it's 1.96. Hopefully we can remember because we've worked through a lot of examples where when we look at 0.025 in the Z table, if I look at 0.025, I'm going to find the negative value, but sure enough, negative 1.96. Any questions kind of using this T table or any confusion that I want to clarify here? Okay, so we got 15 minutes. All right. So I kind of already showed you or alluded to this idea, right? As we go to higher and higher sample sizes, we just get something that looks more and more like a standard normal distribution. As we look at lower sample sizes though, instead of 1.96, we're going to need slightly greater values. Notice if we kept using 1.96 for a student t-distribution with sample size 5, the area is not only is it not 0.025 to the right under the curve, it's as high as 0.068. So we're going to need a much larger value, especially when our sample sizes are low. Okay. I kind of had an abbreviated version of the table here on the slide. We were looking at the actual table that will be provided you on the next exam, but you can also kind of start or print out, start bringing with you to class or having it pulled up on your computer in class, because we'll start using this in class as well. And this kind of reminds you that that last row of the table just reflects you the values you would find looking up those probabilities in a standard normal table. Okay. So we can do confidence intervals, and really the only thing that's going to change is that we're going to still build our confidence interval around whatever sample mean we see. It's just that now we need to look up the student t distribution, the student t value at whatever our degrees of freedom is, that gives us alpha over 2 on each side. Right? And then multiply that by the standard deviation of our sample means, which even though it's going to be like different notation, right? These standard deviations are technically different. Once we plug the numbers in, it doesn't look any different. Right? Once we plug in that sample variance, it doesn't look any different when we're just plugging in the population variance. So we, if we wanted to, could rewrite this to look like this. And we'll still reference kind of this as my margin of error, right? You know, adding and subtracting, just part of the conversation. So we've got everything. I think we should know all the notation here. The only kind of new thing here is that t value where we have to identify our degrees of freedom. So what's our general steps? It's really everything is exact. It's like literally no different other than we're using a student t-distribution now. So let's work through a problem. Okay. So this was just kind of an arbitrary, just giving us some numbers to play around with, also getting us to be able to use that student t-table just a little bit. So let's say I've got a sample of 36, and I see a sample mean of 9. So right away, I know that I'm going to be building my confidence interval around that sample mean of 9. Right? I know I need to look up the t-value that gives me alpha over 2 at a certain degrees of freedom. My sample variance is 324, and my sample size is what? 36. So what's my degrees of freedom? Just n minus 1, so 35, right? And then I can think about, I can build a confidence interval for any level of confidence that I want. So let's say we want to do that for an alpha of 0.01, or what level of confidence would that be? 99%, right? Alpha is the area outside of my interval in decimal form. So 0.01 would be like 1% outside my interval, which means there's 99% inside of it. Okay. So here, my alpha is 0.01. So 0.005 is the area that I want in the tail. So I'm going to have to use that student t-table. I go up here. I already forgot. Our degrees of freedom is 35. So 35 is my degrees of freedom. The area I want in the tail is 0.005. So what? 2.724, right? Should be that t-value I need to get that desired alpha in the tail. So that's the value that 2.7, was it 34? No, 24. I plug in, and now it's just a matter of kind of getting this entered into my calculator. I had to get the upper bound, subtract the margin of error, get the lower bound. Okay. Now notice this value is quite a bit higher. I think the one for the standard normal is what, 2.58. So we're pretty significant difference here, even with a sample size as high as 35. We really need to get those huge samples for the values to start looking more like a normal distribution, or a standard normal distribution. Any questions how I kind of look that value up in the table or I use the table? Okay. So this should have everything, right? We looked that value up. You can calculate, right? The intermediate step is that we can calculate the standard deviation ahead of time and then just plug it in here. Or we can see this form of the confidence interval equation, or, oh, it's not here, it's over here. Or we can see this form of that confidence interval equation. That's what messing this dollar is. You guys, is he not here? No, I saw him like before class, but he's gone now. I don't know where he went. Keep an eye.
Carry your steps in.
I hope she's not lost. So we basically, we can use any form of this equation, or we calculate it ahead of time, and then just plug in this guy here. I think he's. So, not a whole lot new here, really. Like, the process is pretty much the same. It's really just finding that t-value that's the only real difference. Okay? So we got our upper and lower bound. Any questions on that? So, how much time do we have left here? 140. Let's work through one more example, and then I want to show you something in Excel. So let's say that the American Medical Association, right, puts out this thing that the average, physician salary is 175,000. You take a sample and find it's 160, and you find the sample variance as well. You remember that?
Yeah.
Okay, just making sure. Oh, you like to explore? Okay. So we've got our sample mean, we've got our sample variance. We looked at 81 physicians, right? Our sample size. So those are going to be the three values. The only other thing we need is that t-value, right? So we'll take our sample mean of 160,000, add and subtract some t-value. I'm kind of worried about that in a second. And then multiply that by the standard deviation of our sample means, which should just be our sample variance of what? 324 million over 81. So I need to find this t-value that gives me alpha over 2 and have the specific degrees of freedom. So this would be like a potential IQ question I would ask, right? But looking at this, I want you to respond with which one of these values or which one of these answers can't be correct, okay? So stepping away from the computation for a second, looking at these different possible output values for the confidence intervals, based off of that sample mean of 160,000, you should be able to rule out one of these answers right away. So look at them carefully. Think about where the location of the sample mean should be. And one of these answers you should be able to rule out right away just looking at the lower and upper bound. So give you a little bit of time to kind of look over these. There should be one answer you can rule out right away, and that's the one I want you to respond with. So which answer can you rule out? So think about where that value of 160,000 should fall in each one of the confidence intervals, if they were in fact correct. All right. If you haven't gotten an answer in, take your best guess here. We'll talk about it. There's just 12 of us here today. Okay. So what should be true about our sample mean in relationship to our lower and upper bound? It should be exactly in the middle. Which of these is not exactly in the middle? All right. I look at C, 160,000 is only like 4,000 away from the upper bound, but it's 14,000 away from the lower bound, right? So it doesn't exactly split that confidence in the middle, so we could rule out C right away. From there, it's just a matter, we actually have to, if we wanted to look up the actual value, our degrees of freedom would be what? Yeah, 81 minus 1, or n minus 1, so 80 degrees of freedom. My alpha is 0.05, so the area on either side of my confidence interval would be alpha over 2 or 0.025. So I go to that t-table, degrees of freedom of 80. The area I wanted in the tail was 0.025, so I'm going to scroll down here in this column. So I get to 80, 1.99 would be the t-value that I need to plug in. Now we've got everything that we need, right? And it's just a matter of I could calculate the intermediate, use that intermediate step, calculate the standard deviation of my sample means, plug everything in, right? And end up finding the lower and upper bound of 156,163-ish, 164. So really similar process to what we were doing before with confidence intervals. It's just now we're going to have to look up a whatever it is, t-value instead of a z-value. Okay. Now, these are useful, right? In this context, if the AMA was saying the average starting salary is 175,000, I could turn around and look at them and say, with 95% confidence, I can actually tell you, no, it's not, right? 95% confidence, the true, mean starting salary is somewhere in this range. Okay. Any questions on that before I go to Excel one last time before we end class today? So you don't have to worry about reproducing this. And I think I put this up on Canvas, but it's just something I think is a little bit interesting and maybe really convinces you of what we're doing with confidence intervals, okay? So I had like all this data of every student I've ever had and what their kind of integer grade, like grade round to the nearest integer was, right? So I've got what? 430 students in this data set. I can find the true population mean, and I can find that true variance, right? This is based off the population data, okay? Well, instead what I then did was I said, okay, look, I'm gonna take 1,000 different samples, right? 1,000 different samples of size 50, okay? I use this random number generator in Excel, which you don't have to worry about. We're not going to use it for anything in this class. But it basically, every time I click on it, notice it's generating a new set of 50 random numbers, right? And then picking out those students and putting them in my sample. I then kind of made it all into one cell. I just wanted to show you the random number generator was going on there. But really, every time I click anywhere, all these are updating because all my random numbers, it's generating new random numbers. So I'm constantly getting a new set of 1,000 different samples of size 50, okay? From these samples, down here, I calculated their sample mean, okay? Then I used that standard normal distribution because I knew the population variance to find that z-score that gives me alpha over 2 on each side. And then I'm looking at the lower bound, so I took the sample mean and subtracted my margin of error, and then multiplied by the square root of the population variance divided by my sample size. So these cell references, we're really just referencing that true population variance and the sample size of each one of these samples, okay? So that gives my lower bound. I had the same thing, but I added it to get my upper bound. And then I just said, okay, I'm gonna create this check. Is my population mean in this interval? So I look at 75 to 86, that true population mean of about 80, sure enough, it's in that interval, so I put a 1. I then did another sample, right? Calculated its mean, created the lower upper bound, said, okay, and basically all this was doing was using if statements to see, is it greater than the lower bound and is it less than the upper bound, right? If it is, it's somewhere in my confidence interval. So I've got 1,000 different samples. You can notice a lot of them include confidence intervals where the mean is included. Let's say if there's one. Here's one, right, where the upper bound doesn't quite make it far enough and the population mean actually isn't in this confidence interval. Okay. So then what I did was I just used the sum function to count up how many ones I had, which really was telling me that out of 1,000 samples, how many of them had a confidence interval that included that true population mean. Because I can cheat here. I've got all these samples, plus I have the original population data. So I can see that 986 of them did out of 1,000. So the percent of these confidence intervals that included the population mean is floating right around, what, 98.6%. 98.7, 98.5, 99, 99.2. So it's not going to be exact, but it's a good way to show ourselves that whatever alpha level we chose, so the number of standard deviations I was going out was using the alpha of 0.01 or the confidence level of 0.01, then I'm going to get the proportion or the percent of samples that include that population mean will be basically the confidence level that we were talking about before. If alpha is 0.01, we see 99% of our confidence intervals include the population mean. I can even show you, I could do 0.1. And because I referenced that alpha cell when I was looking for the Z value, notice now the proportion of these confidence intervals that include the mean is going to float right around 90%. Okay. So this is kind of a way you can prove to yourself that this is going to hold. My time is up for the day, so I'll let you guys get going. If you have any last minute questions, those are homeworks, I'll try to be keeping an eye on my email the rest of the day. Otherwise, have a great weekend, and I will see you on Monday.